Can you hear me okay? If I talk like this, can you hear me? On Zoom.
Yes.
Thanks.
All right, I think we can get started now. So thanks for coming. Good evening, and I would like to briefly introduce Nicholas's journey so far. Nicholas Saul Rui, the first of his name, was born and grew up in San Diego, California. Nicholas has earned his bachelor's degree in physics and astronomy at the University of California, Berkeley. Go Bears! He joined Caltech in 2020 as a grad student in the physics PhD program and has been an NSF graduate research fellow. Nicholas's research focuses on the physics of stars. Throughout his PhD studies, he has published 6 papers as the lead author and many, many other co-authored publications. He's also the founder of the ARC Seminar here at Caltech, a student-organized journal club that has been running since 2021, helping peer grad students share their scientific ideas, digest classic papers in astrophysics, and most importantly, embezzle free snacks every week. Speaking of Nicholas as a colleague, I would like to quote one old Korean poem. Do not walk in disarray on a snowy field, for the footprints that I press today will become the path for the one who follows. Yes, Nicholas to me was one who walked ahead of me in the snowy plateau of academia, punching through piles of snows for everyone and willing to share all the knowledge with everyone. Even though we work in very different fields, I have always learned from his scientific enthusiasm as well as his professional mindset and attitude. Nicholas was not only a great colleague, but also a considerate friend and fun office mate who will sit down with me and for 3 hours just complain about our lives without getting anything done. And I'm happy to tell you that Nicholas has actually completed his closed room defense 2 hours ago, but he's not a doctor yet in our hearts yet. I believe he will be so by the end of this talk he prepared for all of us today. So I'll put Nicholas on the stage. Please welcome him with a big applause.
Thanks very much to Dr. Kim. So hi everyone. My name is Nicholas, as Yunsu said, and I think even if he hadn't introduced me, like people here know what my name is, which is great. This is a very academic, first slide of my presentation, which I showed to my committee with the name of the talk switched out. But I thought that before I got to like the scientific part, I'd like to go through a few frequently asked questions because I know that this is, many people who are in academia, some people online are not. And so it can be kind of confusing what exactly, the timeline is and what this all means. And I thought I would address some of these. And I hope that it's appreciated by the fellow grad students as well. So we can start with this. What is this exactly? So as Yunsu said, I'm already done with my defense, so you don't have to wish me good luck anymore. It's all over. And so the way it works is I've basically been grilled sort of for 2 hours about the research that I did in my PhD. And this is just like, I hope, something like a victory lap or something. And there's some hope that I can let people in my life know what exactly I've been doing for the last 5 years. And they can decide for themselves if it was worth it. So, yeah, so this is my thesis offense. This is the next one. So how are my classes going? And like, what's my GPA? Okay, so people here are laughing, they're giggling so they know what I'm gonna say, which is I haven't actually taken a class in 3 years. And even when I did take classes, I cared about them less than, well, I was gonna say than I probably should have, but I think I cared about them exactly the appropriate amount. And so, I've like, my body has kind of lost track of when final season is and stuff like that. It's long been gone. Oh, this is loud. Let me just leave this call. Sorry. There's some feedback here, so. Okay. The next one is like, what's grad school like? And oftentimes I get this question from people, which is like, oh, like I should go back to school. Like that would be great, like maybe I should go back and like do a PhD myself. And what is it like exactly? And so, I think opinions vary a little bit. But I think the one thing that I do want to say about it is that grad school is like not really like school in any real way. I mean, at the beginning, yeah, you take a few classes, but if you're wise, you don't care about them. And I think it's more, I think it makes more sense to me to think about it as like an apprenticeship. And so in particular, it's like you're a blacksmith, right? You want to be a blacksmith. So you go to like the best hammer maker in the world and you're like, I want to learn how to make hammers. And so the way that you learn how to make hammers is you kind of follow in your advisor's footsteps or like the master's footsteps. And then you like learn how to make hammers and people come to you and like they actually ask you to make hammers and you make hammers for people and they're actually useful. Like they're not the best hammers, right? But you learn. And then after about 5 years, it's judged that you're a good enough hammer maker to kind of make it on your own. And then this is basically what this is. Okay, so I've been basically trying to make hammers, making pretty crappy hammers for 5 years, but then it's been judged that they're like tolerable. So the next one I think is a little bit more serious, which is I get this a lot. Wow, you're so very smart. I could never do that. I actually get this a lot. Like I was so interested in space and astronomy as a kid, but I could never like hack it into math. I don't know how people do it. The answer is I'm very smart. No. So like this is not a comic designed for this particular topic, but I think it's pretty true, right? So if you really, if you think about what Dr. Kim just said about me, I spent 4 years in undergrad learning physics and astrophysics, and then I spent another 5 years in grad school, which is this is the culmination of that, which means I've been doing this for 9 years. So you have to be like kind of good at something if you do it for 9 years. And it's true that some people might be have a leg up or not. But it's more true that like it's a function of your interest, right? If you're put your mind to it, then like you can get anything done. And the reason why I kind of want to really talk about this is because like physics has this like mystique about it. It has this like genius complex about it. So people think like you're born with the ability to do physics, like you're born knowing what a quantum harmonic oscillator is or the WKB approximation, right? Whereas in reality, it's something you practice just like anything else, right? And if you're not good at it at the beginning, it's just because you didn't study it, yes. And if you're interested, you can do it. And that sort of like attachment to identity can be kind of a problem sometimes because sometimes it can exclude people who look at the past history of like old white men who do physics by themselves in a room and sound like they don't talk to other people and think that they don't look like those people. And conversely, you get people who fit that category, who very often send you emails, of which this is the latest one. It's called Cosmos and Dragons, and then it has like a theory about something, I don't know. And attached to this email was actually a 279-page PDF, and I'm happy to say that my thesis is 1 page longer than that. That's why I have a PhD and they don't. Let's do rapid fire now. Yeah. Do you like astrology? No. Are there any applications to your work? No. You want to be an astronaut? No. Do you like Interstellar? Yeah, actually. Pretty good. It's a pretty good movie. Actually, so Kip Thorne is one of the faculty here, and he was like one of the lead science advisors on that movie. So that was pretty fun. And then like, some others, yeah. Cool. Okay, let's actually like talk about something fun. Oh, one more. So are you like Sheldon from Big Bang Theory? I actually get that one a lot. And that's very offensive because I'm an astrophysicist, which means I'm more like Raj. So, just keep that in mind before you open your mouth who you're talking to. What am I going to do after? So I'm going to be going to Princeton, actually. I have a very nice weird situation where I go to Princeton for a year and then I move to Northwestern. And hopefully it's been guaranteed that I can be at these places for 6 years, but I hope to not take that long to find another job. And I have the NASA Hubble Fellowship, which means they gave me my own hexagon and everything on this picture as is tradition. So okay, so back to the actual science. Okay, so this is this very academic sounding title. And I don't think it's particularly appropriate for this particular talk. So we can rephrase this, color coded and everything, which is how do stars which have merged and stars which are magnetic, how do they sound, right? And what does that like mean exactly? Okay. But I thought before I go to my actual topic, I'd like to sort of talk about what it means to be an astrophysicist. I'm a theoretical astrophysicist, but just being an astrophysicist in general. And to do that, we have to remember that astrophysics is a kind of science, right? That means that I'm a scientist. I'm a scientist in a similar way that a chemist would be a scientist, right? Like this one. And so, you see this diagram a lot in your, in like, in books, right? About like every textbook that you read, like from like first grade to like 12th grade, like always, no matter what the science textbook is about, it has like a chapter at the beginning, which is like, what is the scientific method? And you're like, well, I've never heard of that before. And it has like a diagram like this, and it has something like observation or something like experiment. Okay. And as a chemist, you might ask some questions, and you might have some hypotheses. Like, what happens if I do this? I mix some chemicals and then something happens, or like, I don't know what happens, but I think something should happen based off of my theory. And then you actually do that experiment. And then something happens, and then you have some conclusions, and they might not be what you thought, but okay, you can like test these things. So as an astrophysicist, you're a scientist as well, so you'd like to go through this process as well, and you ask very similar questions to Sasha in the back, which would be like things like, what happens if I put however many that is, 4 times 10 to the 30, I guess, pounds of hydrogen gas in one place, right? So that's a very similar question. It's like, I have some stuff. What happens if the stuff is arranged in a certain way? Okay. The problem is that is expensive, I think. So the way I like to think about being an astrophysicist is it's like it's like you want to answer some questions like a chemist, but the lab is like, you're not allowed in the lab. It's everything in there is too expensive. You're not trusted with it. But the lab is run by like an aggressive gorilla who thinks that it knows what it's doing, but it doesn't. And so the gorilla is just like breaking stuff and like knocking things over, and like things are blowing up, things are exploding, things are on fire, right? And then you're just watching in horror because all of these like nice chemicals are being like wasted in this way, which is like not scientific. And like, there are no controls and stuff like that. It's just a mess. Okay, but the point of astrophysics is that you can be clever. You can say, oh, look, well, like over there, like that mess just happens to be however many pounds of hydrogen gas I just said, in one place, And that's because like, the gorilla is doing all this crazy stuff, not trying to design an experiment for you, but by virtue of the things that it randomly makes, you can answer these questions. Like somehow we know the answer to what happens if you have that much hydrogen gas there. We didn't conduct that experiment. We can look at the stars and learn the answer to that question. Right. And so in that way, we're sort of like Sasha. So yeah, that's what it looks like. And so in astrophysics, we're far away from everything, right? The way we look at something like the sun, or the way we really learn about almost anything outside of our solar system, comes from electromagnetic waves, also known as light, for the familiar first name basis. And that's great. But as Yoon-Soo said, as Dr. Kim said, I'm a stellar physicist, which means I like to answer questions like what happens if you have a lot of matter in one place and it forms a star, right? The problem is that if you get all your information from light, or most of your information from light, stars are not transparent, okay? So you can't see inside the star. You can see the surface of the star because the path between you and the star is transparent, but you can't see inside the star. And that sucks for me because I'd like to know what's going on inside of a star. I don't just want to do experiments and see the surface of the star. And again, most of our observations come from light. So you might be interested in like mapping out stars with interferometry, looking at other galaxies, looking at the cosmic microwave background, this supermassive black hole, or electrical engineers out in space. But this is all surface level, And so one thing I like about astronomy is that even though like things in space look very different, they behave very differently, they're on totally different scales. It's not about like making things more complicated. That's not really our job, contrary to reputation, right? What we really want to do is like understand things in the simplest way possible. Even though those systems are very complicated, we can try and import some intuition from everyday life. So this is an astrophysicist, my advisor Jim, who's in Japan at the moment, and he's looking. Let's say he's looking through a telescope at a bell that's far away. And by looking at the bell, he can learn a lot of things, just like when you look at a star, he can see that the bell is like bronzed, the color. If he can resolve it, he can see what shape it is. However, if he hears the bell ring, now that's something entirely different, because I think even without being able to explain why, we know intuitively that if I ring a bell, and it's solid all the way through, or if I ring a bell that's hollow, they sound very different, right? Like if I made a hollow bell, that'd be great. If I made a solid bell, like people would be mean to me about it. And so somehow by like listening to the bell, you learn information about the interior of the star, of the bell. And it's the same with stars, right? You can learn information about the interiors of stars. Well, there's not actually literally sound that's propagating from you to this from the sun to you, the star to you. But there is a sense in which something can ring the star in the same way that a bell rings, and then light can kind of bring that information to you, right? So you can see stars wiggle in brightness as the surface temperature changes, and this is basically a reflection of waves inside of the star, right? And the key insight here is that even though stars are opaque to electromagnetic waves, opaque to light, they're transparent to fluid waves oftentimes. And so by using those as the messenger instead of light, or in addition to light, you can learn things about the interiors of stars. So that's a technique called astroseismology. Stars like the sun oscillate, well, stars oscillate for various reasons, but stars like the sun oscillate because of near surface convection. So basically the surface of the sun is sort of like a boiling pot. You know, if you've ever boiled a pot, you know, again, this intuition thing, then you can see that you get these like cells which kind of go up and down, and that like just randomly stochastically rings the star. And this is an actual movie of the surface of the sun. It's not a simulation, right? And I've roughly put on top of it like to scale the size of the United States, so you can see roughly how big these blobs are. They're about the size of Texas or so. And yeah, so real data. It turns out that, however, that other stars, you know, so the sun is like a really nice star because we can actually like look at it. Please don't look at it with your eyes, but somehow we have instruments that can look at it, and we can like kind of resolve it very carefully. But there are stars that are very much farther away, that we know have very kind of similar structures in the sense that they have these convective blobs that ring the star. But that we can't like really see their surfaces, but somehow we can still measure the star quakes inside of them. So this is an example of a red supergiant. I'm really going to talk about red giants, which are similar to this. You know, the cells on these stars are much bigger. These stars are much bigger in general, right? But they're similar in the sense that they oscillate for very similar reasons. That's what I mostly think about. So just to give you a sense of scale, I'm really fond of this example. So I think a lot of times in astrophysics, you think like, oh, things are really cool because things are just much bigger than us. Okay, but like everything is, so you know, whatever. But I think in astrophysics is very nice because there's also not just difference in scale between stars and us, but difference in scale between stars and each other. And in general, there's a lot of scale separation in astrophysics that you have to think about. So let's just scale everything down because we want to have some intuition, right? So let's say we scale the sun down to the size of a marble. So that's like a holy ball, but like just imagine a 1 centimeter tall marble, right? So and this thing has, you know, some amount of mass. So the sun basically glows because it's burning hydrogen. It's burning hydrogen in its core, and then eventually at some point the core runs out of hydrogen. The envelope doesn't. The envelope's still made of hydrogen, but the core is burned into helium through nuclear fusion. And when it does so, it goes up the red giant branch. What happens is this helium sits in the middle. It doesn't really do anything. But the envelope is basically, there's like a little shell around this like core that's not doing anything, that's burning hydrogen. And that actually causes the star to expand a lot. As it expands, it keeps expanding as more and more of this hydrogen gets turned into helium, until eventually the star expands by a factor of 200, right? Which in this scale is the size of a car. Right, so this star, all of this mass, which fits in a marble, because of this burning, grows into a sphere about the size of a car. Same amount of mass, much lower density. And about half of that mass is actually stored not inside, you know, so half of that mass is in this big envelope, and then the other half of the mass is in a small, dense helium core. And at this point, the helium core is around the size of the Earth. And the Earth is about 100 times smaller in length than the sun. And so on this scale, if the sun is a marble, this core is maybe like a ball about the size of a few hairs across. Right, so half of this marble went into a ball about the width of a few human hairs, and the other half is like the size of a car. Right. And so like this sort of object, this big star is called a red giant. It's the kind of thing that I'm interested in, what most of my PhD is about. And stars, they range for many different reasons. The envelopes of these red giants, you get something called pressure waves. These are basically the waves that are communicating information from me to you, right? And this is just like an example. This is basically, you squeeze some gas and the gas pushes back, it fights back. And then as a result of that, there's some propagating disturbance, which brings information, right? But in addition to that, there's a different kind of wave, which propagates in stars, which we also have some intuition for, but we should try and see why we think that should exist. Okay, so I think this is Dr. Kim and a very handsome lookalike. And I basically use them to represent fluid parcels which are less dense and more dense, right? So Yunsu is not dense. He's actually a really nice, smart guy. So I've made him the light fluid, and then I've made his lookalike the dense fluid, right? And we can ask what happens, like in stars, like it's not one homogeneous mixture, like some fluid is actually denser than other fluid. So we can ask the question, what happens if you take two different densities of fluid and stack them on top of each other? Okay, well, if you put the light fluid below the dense fluid, right, the light fluid wants to fall because there's gravity, but the dense fluid also wants to fall. So who wins? Because they can't all fit in the center of the star. Like one of them has to fall better than the other one. Like they have to compete. And then it turns out that if you're denser, then you win. So in this case, Yunsu loses, and then he has to go to the top. And this is called convection, right? So this is kind of a runaway process. You sit there, but then if you're nudged up and down, you can be less or more dense than you can be. If you're let's say you're nudged up, you can be less dense than your surroundings by that point, and then you can just kind of float up. And this is like what happens in the outer layers of the sun. Like the sun has an outer region which is like a convective envelope. It's sort of like, again, what happens when you heat up a pot and it's boiling. But now if we arrange things the other way, then if I sort of put Yunsu, the light fluid, on top, and then I nudge him down, right? Well, then he's now like denser, now he's like lighter than his surroundings. So what happens is like Yunsu pushed down, but then the lighter fluid's like, hey, I fall better, remember? So then like there's like an oscillation, like the dense fluid kind of falls in, and then like there's like a wiggle. It's kind of like a rubber duck floating on the surface of a pond or something. Like you nudge it down and then it gets pushed back up. This is called buoyancy, right? Like buoyancy is just gravity, but like some fluid is like trying to compete with other fluid. And these sorts of waves are not called buoyant waves, unfortunately. They're called gravity waves. So we have a domain over this word. Yeah. So a good example of a gravity wave, called a surface gravity wave, would be like waves on the ocean, right? These don't get restored because you're squeezing fluid and the fluid wants to push back. These are actually much lower frequency waves. Like, sound travels very fast, but these waves, you can just watch them evolve, right? They're lower frequency oscillations, which are restored because of buoyancy. So those are surface gravity waves, but then there's also what's called an internal gravity wave, which is actually more what I'm interested in. This is an example I'm very fond of. It's called a lenticular cloud. And the reason why these things form, these are like pancake-shaped clouds. They form because air sometimes flows over a mountain. It excites this kind of gravity wave, and this gravity wave has this kind of pancakey structure, right? It's like very flat, kind of. And as a result of that, some of the regions of this oscillation get to a low enough temperature that they turn into they go below what's called the dew point, and then you can see that they form clouds. They kind of condense out the water vapor. And in red giants, it's pretty interesting. They have both pressure waves and gravity waves. So the envelope and the outer layers, they have pressure waves, like just the kind of sounds that you're hearing. But those actually are like interacting with gravity waves in the core. And why would that happen in red giants? Well, it's because, as I mentioned, the cores of red giants are like super dense, right? Whereas the envelopes are like not as dense, right? And I said that gravity waves are like the lower frequency, sort of longer timescale kind of oscillations. But like the core is so dense that like everything is like low frequency compared to that. And so one frequency may be high frequency compared, high frequency in the envelope, but also low frequency in the core. Now, how do we actually observe these star quakes? Well, first, what you do is you just like watch the brightness of the star change. So you might see like a curve like this. It's kind of like hard to interpret. It's a little random. Okay, but you could use a technique called Fourier analysis, where we basically say, well, we can pretend that instead of like looking at this in time, what if this is just like a combination of notes? You know, what kind of combination of notes should I have to put together, right? So I can break this signal up into like kind of perfect tones, right? Perfect sinusoids, perfect wiggles, right? And then I can plot that. And you can see in this case, this is much easier to interpret. Now we see like these spikes, right? And these spikes are things that we can actually very precisely measure in stars. They're called oscillation modes. So this is an example, actual example of the oscillation spectrum of the sun. When you do this, right, you see that there's like a really fine cone in oscillation modes, which have a lot to do, when you measure those frequencies very precisely, you have a lot of information about the structure of the star. And as I said, other stars like red giants oscillate for very similar reasons. So it stands to reason that their spectra would look very similar. And indeed they do. This is an example of a red giant. You can see that that signal is very hard to interpret. But if you do this procedure, then you see something very similar. Like this envelope kind of like, you know, that's peaked in the middle. And then it's like, you know, there's a cone of modes that you can measure the precise frequencies of. And so one part of my PhD was basically saying, well, you know, you have three different stars which might look very similar. So are they actually the same kind of star, or are they different kinds of stars? And it turns out that there are several kinds of evolutionary stages which look very similar. And then there are also things which can happen to stars that can make their interior structures very different, even if they look the same. Okay. And so to sort of understand like the different things that can happen inside of a star, we can maybe examine what's going on in the core. Okay. This is just an example of three people who look very, very similar, but are in fact different people. So if you only look at them, you can't really tell them apart. But if you listen to them, then they say different things, and then you can tell them apart, right? But this is the basic intuition that we have from everyday lives. I'm sure everyone's had to do a lineup like this. And so to understand like what can go wrong and what can happen inside of the structure of a star, right? We can sort of think about what matter is made of. And so broadly speaking, matter is made of like nuclei with like electrons, that are orbiting them, right? And we often think, well, the electrons are like less massive, but it turns out for quantum mechanical reasons, electrons actually take up more space because they're less massive. And so, for example, a carbon atom might look something like this, right? Where like this is actually like, Isaac, who's the nucleus, should be much smaller actually on the scale. Where you have 6 electrons, but they're like so big that they basically form this quantum mechanical cloud. Okay, but they're bound to the nucleus. But in a star, it's very, very hot. So the temperature is so high that the electrons are not really bound to the nuclei anymore. They just kind of like behave like separate gases almost. And this is what's called a plasma. So it's like this fourth state of matter, right? It's just when you're so hot that the electrons and the nuclei separate. And this is what's called a non-degenerate plasma. So you can see in this case, the electrons, which are represented by David, and the nuclei, which are represented by Isaac, they're basically like taking on like a ton of different energies, right? And like they're kind of like they're scattering with each other, but they're in some sense like taking whatever states they want, right? They have some temperature. But turns out in very dense environments or in very cool environments, so such as in the core of a red giant, you get this separate situation where the electrons become what's called degenerate. So what does this mean exactly? So I like to think about this as like, suppose this is like a room, like a pretty packed room, like a small room with a TV in the front. Okay. Now, if the TV is really big, then people don't really care where they sit, and they just sit anywhere, and then no one's fighting for seats. But if the TV is really small, then like everyone tries to cram towards the center, but like not everyone can actually everyone tries to cram to the front, but not everyone can get to the front. Okay, and then so they are forced, even if the TV gets much smaller, they can't actually pack any farther in, right? And so similarly, when the temperature gets low enough, electrons actually run out of states to continue to lower their energy. And so they basically just pile up at 0 energy, but they literally can't decrease their energy anymore. Now, in this case, in the case of like, red giant cores, Isaac doesn't mind because it turns out nuclei don't take up as much space. So even when the electrons run out of space, the nuclei don't. And so the nuclei remain non-degenerate. But it turns out that in the cores of red giants, this sort of packing thing that's going on is actually responsible for the pressure support in the star, right? So unlike in a gas, when like you increase the temperature, you increase the pressure. In this case, the pressure doesn't depend on the temperature pretty much at all. Now, if you actually listen to the gravity waves inside of red giants, you can tell these stars are different actually. These are 3 different kinds of stars. Actually, I was concerned in this project about the difference between these two, right? Which is, there's a little bit of nuance here, but basically the statement is that it turns out that when stars are around the mass of our sun, or maybe less than about 2 solar masses, when they go up the red giant branch, their cores are this degenerate matter, like they're super dense. But it turns out when stars are more massive than about 2 solar masses, the cores are actually never become degenerate, right? And so you can hear the difference because one is of course much denser than the other. And then the example on the right is it turns out these stars can also, they eventually burn helium as well, which I'll talk about in a second. And that also sounds very significantly different. But this is pretty interesting because you can hear how massive these stars are as well. So you might find a star that you think should be born. You observe it today and it has more than 2 solar masses, right? But then its core is actually dense, right? So if stars which are born more than 2 solar masses have to have non-degenerate cores, and you find one that has a degenerate core, that means that it had to have been born with a lower mass, right? So you can hear this star and you can tell, like, you weren't born with the mass that you have. Like, you must have eaten your brother or something, right? And so you're more massive today, but you didn't start off with that, right? Because you didn't evolve like that. And I can hear it. And there are many different ways in which stars can interact. That's only one, just engulfing your companion. But there are also situations where stars basically strip the matter off of their companions. Where stars basically strip the matter off of a red giant, and then what you're left with is this core of helium. Again, this helium ball is degeneracy supported, right? The electrons are crammed in. And if the sun is the size of a marble, this thing is a ball the size of a few human hairs across, yada, yada, yada. This thing is called a helium white dwarf. It turns out like one thing that can do it is like a companion can basically, kind of strip the envelope off of a red giant and leave this stripped core, which is called a white dwarf, as I said. And then they can again merge. And when they merge again, basically this matter, from the star accretes back onto the white dwarf. So this is kind of weird, right? You took this red giant, you removed the hydrogen off of it, and then you put the hydrogen back on. Like, what difference does this make? Well, it turns out that the core is actually cold, right? Because even though the core is basically like degeneracy supported and like very dense, it's also very, very hot because it's always touching a shell that is burning hydrogen, which happens at like 30 million Kelvin or 30 million Celsius. But if you take the envelope off of a red giant, it will cool down. The core will cool down. And then if you add hydrogen back on, it turns out that it takes its time to heat back up. Right. And this thing actually evolves similarly to a red giant, but it has some weird properties. It sounds very different, but I think my favorite part of this project was actually that when it starts to ignite helium, it does something very, very strange. And so that's this outcome. And so just to kind of understand this, this is again a schematic of the core with the envelope on top of it in a red giant. And then this thing eventually it gets so dense, the core gets so dense, the envelope is around 200 solar radii. And then the core realizes that it's hot enough to burn helium, which is about 100 million Celsius. And so we can kind of go back to this example to try and understand what happens, right? So when you have non-degenerate plasma, but you have nuclear fusion, this is actually a pretty stable process. Now, why is this? Because when you burn some hydrogen, you basically release some energy, you release some heat, but that heat basically heats up the plasma and then it increases the pressure. right? So which causes it to puff up, which causes it to cool down. So as soon as you add pressure, it kind of like turns itself off, which is great, right? You know, it's stable and all that. However, on the case of the right, the pressure doesn't depend on the temperature really at all, because the pressure is like totally caused by, you know, David being packed into the lowest energy states, right? The electron degeneracy. So let me just do this. So this is what it would look like. Yeah. But on the right side, when the hydrogen burns, it increases the temperature, but the pressure doesn't actually go up. So the hydrogen realizes it's hotter, and when it's hotter, it burns even more. And then it burns even more, but like the pressure's not changing, so it keeps going. And this is actually a very, very violent process. It's like 0.3 times, 0.3% of the energy of a supernova or something like that, but like buried inside of a star. Or I think it's the luminosity, actually. Energy, luminosity, energy, I think. Anyway, so this runs away until you introduce so much energy that you can cause David to increase in temperature, right? And then the pressure support is lifted, and then the star can finally ignite helium stably, right? This is called a helium flash. Yeah, okay, so here's the fact that I wanted to say. So it's 0.3% of the energy release of one of these type 1a supernovae. But it's like buried inside of a star, so you can't really see it. So what happens, you know, what does that mean for these like weird, like stripped star mergers, right? So normally what happens is that once you reach this 200 solar radii, you go through this helium flash, and then it turns out you shrink it back down to about 10 solar radii, which in the scale of like the sun being a marble, this is about this sphere the size of a deck of cards, right? And this thing is about 70% hydrogen, 30% helium, basically the same composition as you started, except for the core. But it turns out that when you have this cold core, it takes so much more energy to release, to lift the degeneracy, that like hydrogen can burn sort of more vigorously, it releases more heat, and it can kind of excite what's called convection, which we just explained. So, you know, this is just recall this, right? And that convection becomes strong enough that it can actually mix part of the helium into the envelope. And turns out as a result of that, for reasons I won't really explain, the star ends up being a lot brighter. So this star, you know, it would be hard to tell by looking at it actually that it has 50% hydrogen or 50% helium, let's say. So it's in the same evolutionary stage, but it's maybe like twice the radius, right? And yeah. So another part of my PhD, which I'm quite enthusiastic about, is the question like what happens when you have these like buoyancy restored gravity waves, but in a realistic environment where a star might be magnetic. So of course, this is like a very complicated phenomenon, so we often leave it out. But stars are very often magnetic, and so we want to ask the question, well, like what happens when the gravity waves propagate through like a strong magnetic field? And so it turns out the result of that is you add an additional force, right? If you add an additional force, like you stiffen like a bell, it's going to bring out higher notes. And the same thing happens with the magnetic field. It turns out it introduces something called the magnetic tension. Magnetic field lines are sort of like, you know, strings that don't like to be, you know, pulled like this. They kind of restore back like violin strings almost. And we don't really, you know, it was really hard, you know, how do you actually predict what notes the star brings at? You know that it should be stiffer, but, you know, higher frequency, but you don't know why, you know, and how. You don't know how. We can take a kind of borrow from a different phenomenon, which we do know how to deal with, which is rotation. Turns out for gravity waves, the force that is most relevant when talking about rotation is the Coriolis force, which is not really a force, actually. So if you're watching a rotating star, then like you know that like if something doesn't experience a force, it should go in a straight line, right? So this is just us sitting outside of the star. And you can see that if something is thrown, it follows a straight line. But if you're sitting on the star, then your perspective shifts because you see that the object is basically curving. It's not curving because there's actually a force. It's curving because you're not sitting still, basically. But to the star, it doesn't matter if it's a real force or not. It experiences a similar force. It experiences this as if it's a real force, and that also changes the frequencies of the oscillations. And to understand like why this problem might be difficult, we can kind of use Kyle as an example. So we want to understand. So Kyle's my office mate, and we want to understand what Kyle sounds like when he's underwater. So I know this from experience. Anyways, this is the system we're trying to model. Okay, but suppose I didn't know that somehow, right? What I might like to do is say, well, first I understand what Kyle looks like when he's not underwater, what he sounds like when he's not underwater. So this is Kyle's natural habitat. And if we put Kyle in a pool, then it would be pretty simple, I think, to predict what Kyle sounds like when he's in the pool, right? Because every surface of Kyle's body is contacting water, and so we can kind of add up all of the influence of the water across Kyle's body in order to figure out what he sounds like. And it's probably not going to sound that different. Like it's going to sound different, but we can figure it out, right? Because we know what shape Kyle is supposed to be. And even if we can't do it, with math, someone smart can use a computer and like work it out. However, if we put Kyle at the bottom of the ocean, that would be something really different. Because it's not just that we know Kyle's shape, and then we just have to add up all the influence of the water on Kyle's body. Now Kyle's shape has been substantially deformed, and Kyle's no longer like sounds recognizable. Like it's not just that we can. It's not just like that we can like. It's difficult to put in a computer. Like we don't even know what to put in a computer anymore. Like how do we work out like what Kyle's shape is, right? Because now we have to figure this out. Right. So this is called like being strongly perturbed versus using perturbation theory. Okay. So we can try and play a trick. We can ask what happens when we're dealing with a magnetic field, but it's so strong that it disrupts the shape of the gravity wave. Oh, poor Kyle, by the way. So again, recall this is what gravity waves are. So we can ask like, okay, what do the gravity waves look like here? And the intuition is very simple. Again, this is what gravity waves look like on the Earth, and you can see they have these very pancakey structures. And you can make a simple approximation. You can say, what happens if instead of being almost like pancakes, like almost like perfectly flat, they are perfectly flat, right? If you say that, then all you have to do is zoom in on a little shell. If you zoom in on a little shell, you don't have to know the whole structure of the star. You only have to know about like this two-dimensional problem on a sphere. And so you can solve that problem. That problem is significantly easier because you don't have to know anything about the actual star. And then once you solve that problem, you can kind of stack the pancakes back up. And so that, once you do that, you can kind of work out the effect of a strong magnetic field, without having to assume its shape ahead of time, or the shape of the gravity wave ahead. And that can cause what's called magnetic suppression, or basically like the muffling of the sound, like dissipates the energy, or it can stiffen the oscillation and increase the frequencies in a way which we can now predict. And this is we call this the traditional approximation of rotation and magnetism, because the original approximation involving just rotation is traditional approximation of rotation. But I do feel a little bit odd that I just made up an approximation and then immediately called it traditional. But I promise this is not my fault. Okay. There are some other things which are kind of interesting. So when I kind of buried the lead a bit because I said, when the star shakes, in a mode, then what you see is basically this oscillation, right? And so you see like this peak in this power spectrum that I showed. But this is not always the case, right? So this is the case when the Coriolis force is very strong, when rotation is very strong. When the rotation is very strong, then your oscillation modes look like this, right? There's some rotation axis, and the oscillations are kind of aligned to it. But it turns out there's sometimes an additional force again. That force is magnetism. And usually people will assume, almost always assume now, that the rotation is winning at setting the direction, the orientation of these oscillations. But I disagree. I would like to understand the opposite regime. It turns out when this happens, you get something called an oblique pulsation, where the direction, the sort of orientation of this oscillation mode is kind of changed. Like this angle of this oscillation mode is changed. And when that happens, the shape of the wiggle in light actually looks different. It doesn't look like this pure sine wave. It actually looks something like this, more like what's called a beat pattern. right? So this is actually looks like multiple nodes stacked on top of each other, but it's actually one single oscillation node. Yeah, and the reason, and but then we can ask the question like, okay, what happens if in addition to having a strong magnetic field, the star is also being wiggled like kind of randomly, like like in the sun or like in a red giant. And it turns out, it's kind of hard to distinguish between two different oscillation modes, two different notes the star rings at. It's hard to distinguish two different notes from one single oscillation mode, which is not aligned with the rotation axis, right? So most astronomers who work on this would probably look at the top and bottom examples and think that they're the same. And the reason why they do that is because they do this procedure where they kind of take the signal and they turn it into like notes, basically. You can see that there are two peaks, one here, in both the top and bottom examples. But if you look at the animation on the right, they're clearly very different. Right. So the top, one on the top, it kind of wiggles back and forth, like it's like kind of not rotating very steadily, whereas the one on the bottom is like processing very, very deterministically, very steadily. And you can see again, if I plot the intensity pattern due to this oscillation, these two are very different. Visually, you can see that, but you can't see it if you apply this procedure blindly, right? So that's why we call this paper not just a phase, because there's a phase in it. You need to retain phase information basically to tell these apart, right? And so this is kind of nice because when everyone's doing something, because there's some conventional wisdom, then you might be able to find your niche. So I think the last project that I want to talk about is basically, well, I like to talk about red giants a lot. They're like one of my favorite objects. But then on the other hand, like a lot of what I talked about didn't really need the object to be a red giant, right? I talked about gravity waves, but gravity waves are on the Earth. Gravity waves are in red giants as well, but they're also in these objects called white dwarfs. I kind of mentioned them before. They're what happens when a red giant is stripped, but they're also what happens when the sun eventually dies without being stripped. And they're basically objects which are about the mass of the sun, but about the radius of the Earth. So this is the scale. That's the sun up there, and then this is the Earth. And this is just a diagram of like various kinds of white dwarfs. So like these objects are like about like this small, but that massive, basically. And these objects, interestingly, also have gravity waves in them. And so in principle, the same physics should apply. The same physics that we worked out for the red giants should also apply in these white dwarfs. And so what do we learn by doing that? Well, it turns out that if you look at white dwarfs, they don't look like they don't sound magnetic, basically, right? They don't display a lot of the features that you would predict if they were magnetic. We can measure the magnetic fields of white dwarfs with like methods such as like spectroscopy. We basically look at quantum effects which are affecting the spectra of these things. But that basically only buys you what would be called like 1 mega Gauss-ish fields, which I think is however many Tesla, I'm not sure. 10 to the 6, 100 Tesla, I guess. And then if you use more sort of precise methods, you might get down to like, 1 Tesla or something like that. But seismology, it turns out, by looking at white dwarfs and not hearing magnetism, you actually know that the magnetic field is quite a bit weaker than like anything you could detect with spectroscopy. And so like these circular points are basically using the traditional method for measuring magnetic fields, whereas these triangles here are like the maximum amount that a bunch of different white dwarfs can possibly be magnetically. And to just give you a sense of scale, like this is the only plot I'm showing, and it's already like kind of dry. The Earth and the sun, they both have average magnetic fields, which are actually about the same. They're about half a Gauss, or like 1 Gauss-ish, which is like not enough for you to feel it, but it's enough for your compasses to work. Okay, so that's basically down here. You can see that we think that we know that some white dwarfs are like no more magnetic than about the Earth, which is very crazy because these things are light years away. Fringe magnets are about there, maybe like 100 Gauss or so. Neodymium magnets, are maybe like, 0.1 Tesla or so, and if you played with those, there's serious business already. And I know sunspots, it turns out, are also about the same magnetic field. MRI machines are maybe about Tesla or a few Tesla, and then if you dial it up about an order of magnitude, about a factor of 10 to tens of Tesla, you can even levitate frogs. So this is sort of, so like MRI machine and frog regime is about the how much you can kind of observationally limit magnetic fields in most white dwarfs, but sometimes you can get down to fridge magnets, which is pretty crazy. Okay, I had some other scientific adventures. Here they are. They're not that important. I do want to say some things and kind of summarize. There are way too many people for me to thank, and frankly, I didn't have time to like think of everybody and put everyone on. But this is my research group, right? We're not really big on group photos, so this is the best that we have. We started during COVID, unfortunately. So this is just an example of one of our group meetings. You can see me looking handsome in the top left. You can see my advisor and some other grad students and postdocs along the journey. And then since there have been many other people who have joined, who I'm very thankful for. And also quite thankful to the friends we made along the way, including my office mates. It turns out for interesting reasons, by coincidence, we all moved into the same office after having independently decided to go to around Joshua Tree at the same time as the aurora. We didn't actually know the aurora was going to happen when we did this. And so this is a real photo of us in front of the real aurora. And we also gave Guido and Kyle Chinese names. I have a lot of pictures. I couldn't fit every single picture that I had, but each of these pictures is a story. And it reflects, as much as you all being here, like how much support I've gotten over the years. And how I really couldn't have made it without you, because quite frankly, I need to get out of my office and someone has to make me. And many people independently made that decision. So I thank you for keeping me alive. And finally, I should really thank my family, my parents in the back, my dog and my sister in that order. They've really been my rock over the many years. They've given me a lot of support. And they don't fall into this, stereotype of forcing me to do certain things. They always let me explore my passions, while, giving me whatever support that I needed and giving me unconditional love. So, it's very, very important. That's all. Thanks. Any questions? This is what they actually look like. Okay. Anyone have any questions? Yeah.
I learned marketing science communication. So as a chemist and sometimes across the business, I'd like to ask, are any of these stellar dynamics directly, do they have characteristic radiation, maybe in the very, very low frequency radio range that's observed?
Yeah, that's a.
You can see the luminosity changing of those kinds of stuff, but is there characteristic radiation?
That's a good question. Yes.
On one of those.
In microhertz.
That seems to be too slow to detect most of the time.
Okay, well, so one thing that I will say, if you're talking about low frequency radiation,
Yeah,
right?
very
I'm not aware of generic radiation of that type, which is in white dwarfs, although there is an interesting new phenomenon, which is called a white dwarf pulsar, which you can ask Yunsu about. So it's basically this idea that for some reason, when certain magnetic white dwarfs are in a companion with a star, then they also pulse just like a neutron star. They basically beam radio waves at you very coherently, very energetically, unlike a clock, like clockwork. And that's one example of low frequency radiation you might get out of an object like this. I'm not aware of it happening kind of like deterministically, but like all the time. Any other questions?
I have a question. I can't figure out how to raise my hand on the Zoom. Like I haven't used this in like the last couple of years. I couldn't find the function. I might have missed this at the end, but could you talk a bit about the work that you're planning to do in the future and how like this might segue into that? I'm assuming your research position next was one where you had to write like a proposal of what you were doing.
Yes, yeah, so this is of the hexagon lore.
Oh.
So I did in fact have to write a proposal in order to earn a hexagon. And so basically, yeah. So I was quite interested in what happens when certain stars interact with each other. Where is this? Where's the there we go. I was quite interested in what happens when stars interact with each other because those stellar structures can look and therefore sound very different. I only investigated in my thesis 2 different ways in which this could happen. But there, you can take like really almost like any 2 stars and then kind of stick them together, and like nature often makes that happen. And so there are very many different kinds of mergers which make very different kinds of weird stars whose sounds we still don't know. And that's basically the topic of the proposal I wrote for this. And then I also have many other ideas for ways in which we can try and probe the magnetic fields in other kinds of stars, or ways in which we can extend our theoretical understanding. So that's more or less what I have planned. And then there was some chat today, actually after my defense, maybe I'll do 3-dimensional simulations. Maybe I'll do what's called population synthesis. What's your opinion? Anyways, so, the world's my oyster. We'll see if I try those things and I like the flavor or not. Thanks. Any other questions?
My other question is how you got into research on stars in the first place, like your personal journey.
Oh, that's
stars something that you were interested like in undergrad? It was before that. Yeah.
So it's kind of interesting actually. In Berkeley, you need to take 2 astronomy classes. Like out of 3, there are 3 different astronomy classes you can take. You need to take 2 of them. So there was planets, there was stars, and there's cosmology. And guess which one I didn't take? So I didn't know anything about stars, basically, except for like the cartoon picture, until I went to grad school. I didn't really choose to come here because I wanted to learn about stars. I didn't really care about stars, but I liked like kind of the vibe of my advisor, like the way that he thought about things. And I think what was memorable to me is on his website, he says something like, he's a stellar physicist, but he says, I'm broadly interested in the vibrations of fluid spheres, gravitating fluid spheres. I thought, wow, that's like a very like fundamental, kind of reductionist way to think about problems, right? Like that's what I want to do, Like I think a lot of times, a lot of astronomers are motivated by like there's something out there and they want to understand it and find it. But for me, I more view like nature as making experiments for us. Like I care a little less that they're out there and a little more that we can learn the physics that's in them. So it's not really about the stars themselves, although they're certainly very cool. I've been Stockholm syndromed, I think.
Okay, thank you. And congrats, Doctor.
Yeah, thanks. Okay, maybe one more? Yeah.
Okay, one last. So, okay, can you go to your 3 Sarahs slide analogy?
3 Sarahs.
The stars, the big stars in particular. The one before that. So you said the one in, so are these all red giants? Because you said the one in the middle doesn't have a degenerate core.
That's right.
So what is going on here? How does this work?
Yeah, so it turns out that when the star is bigger than 2 solar masses, it goes up something which looks like a red giant branch, but the core never becomes degenerate. Right, so the core, like as it grows, like becomes more degenerate as it goes up to RGB. But like for stars above 2 solar masses, they never actually become degenerate. But they're still like these stars like are still the same size. They're still 10 solar radii. They're all 10 solar radii. They look the same. So I claim that this counts as them being red giants because they look superficially red and giant. Yeah, although like it is true that in astronomy, we have this nomenclature issue. Because like we oftentimes usually we discover stuff before we know what it is, so then the observers get to name it some like unintuitive thing. So in this case, they named these stars red giants, but actually, I would say these are all red giants. And I would say that these are something, this is on the red giant branch, this is kind of on the red giant branch, and then this is not on the red giant branch, but it's a red giant. So that gives you a sense for what we have. That's why they pay me the big bucks. They actually don't. Cool. Thanks. I have. Good night.
Dr. Rooney.
I got to sleep now.
Oh, that's you. Yeah, that's me, mine too.